Hi, in this video we'll cover the concept map on thermal, that is topic B1 to 4. If you haven't watched the previous mind map before, I'll recommend you to check them out earlier. That cover mechanics, electricity, and waves. Notice that topic B5, which is pretty much about circuit, has been already covered in electricity. So let's get started. So we'll start the block from here, thermal. And the first thing that we are interested in is how the thermal energy are transferred. It's due to the temperature difference between the two bodies, and that tells us the direction. In terms of the method, I'm sure you all know conduction, convection, radiation. For conduction, it's about transferring Ke and momentum to the adjacent particle. So yeah, physically they are in contact with each other. There's an equation we have in IB describing that. Okay, so make sure you check out all the quantities meaning. As for convection, there's no equation in IB Physics. It's not required. But what you really need to know is really just qualitatively, knowing that it's due to the fluid density. Obviously, the so-called hotter fluid would be of less density, and therefore they will go up, and then the colder would sink because they have a higher density, and so that create a mix of the different fluid, and of course within that there's also conduction happening. The more content we put in is radiation, and the radiation idea is simply, in other words, is emitting EM wave. And so in terms of emitting EM wave, we have developed two laws describing that. The first one is Wien's displacement law, which describes how the maximum intensity of wavelength is correspond to the temperature of an object or the system, and which is related to this diagram. Okay, and so for this diagram, you really need to know that how to read it. Okay, sometimes they will change it to frequency on the x-axis, so you need to know how it's get converted, although usually they will show you in wave. So the so-called peak intensity will be like here, 4x3 for example. When we change from different temperature, as you could see from this diagram, which is really nice, you can see the peak will shift to the left hand side because the wavelength will decrease. At the same time, the whole envelope of the higher temperature is still always higher than the lower temperature one. So for example, if you see the 6001 versus the 5001, the shape is honestly more or less the same. It's in proportion, and therefore at any point of the wavelength, 6001 is always of a higher intensity than the lower temperature 5001, for example. So these determine whether or not the most EM wave intensity emitted by a certain body is, for example, a visible light, which you see something that is maybe red hot, or the flame is in blue color from the Bunsen burner, or something that emitted like our body or the earth emitted as infrared. And in terms of just the quantitative idea of the power, then we have the Stefan-Boltzmann law, which is stated as this equation. Although the symbol is a bit strange that it is in terms of L luminosity, but the more general equation you can see here is power equals to emissivity, and then the constant AT to the power 4. So essentially, this is a more general one, which I prefer more usually. And then if you want to talk about stars, then yeah, you can use that. Notice that the one you see here, which is on the data booklet, is assuming that is having the emissivity E equals to 1. Okay, because they treat basically, or to simplify, they treat it as a black body for the system. Okay, and for the power equation here about radiation, this is not the one you see on the data booklet. You see this one. Okay, but apparently you need to know how to turn to this equation if you want to, or if you understand this one, that's fine. All right, and then with these equations, together with the idea of intensity equals to power over area. By the way, okay, pay attention to the A here and the A here. They are not the same thing. Okay, so for the intensity, the more very general equation here, the A is talking about the area that covered by the virtual sphere. Okay, so imagine as the light, for example, or the sound wave propagated, and then that will reach to a certain distance. That's the spherical area that it reached. While for the power of the radiation or luminosity, this A is talking about the object. So for example, if you have a black body of a certain planet, and that A is the surface area of it. Okay, so it's simply you can calculate by the radius of the planet using the equation, and then you can find the surface area of it. So the 2A are different things. So just pay attention to that. Using this intensity equation, you can then find the apparent brightness, because how we perceive, okay, is a star brighter or not as bright is in terms of what we measure on Earth. So intensity is what we measure. We don't really measure power directly, okay? And so that would lead to this equation here, as you could, if you understand what I just said, then this A under the intensity, the virtual sphere would basically be 4 pi d squared. Okay, d is the distance away from it. And so that's why you have this equation. You can see I have a link here which link basically to astro. Okay, so you can see the topics are also interlocked together. In the exam, you may also expect these are coming together with astrophysics. Now, with this general brightness equation, then we can come up with the solar constant, which is the measurement of the amount of solar EM radiation received per unit. Oh, I'm reading this. Okay, so basically, the most important thing is defined as the intensity outside of the Earth's atmosphere. So that means the atmosphere will have an effect to it. So the one that you see, the number about 1,400 on the data booklet, you can find it, by the way, on the data booklet. Okay, you can use it. Sometimes the question would not tell you that you have to use it. Okay, so you need to just have the awareness that you have this. And this is referring to outside of the atmosphere. So the atmosphere will have some interaction with it, so maybe some of them are reflected and then scatter and then etc. That's something you need to know. As for how that 1,400 is obtained, then you have to refer to this diagram. Okay, it's a little bit abstract than you think, and then I addressed that in another video. So if you want to go back to visit that again, then make sure you check it out. It's something to do with the 2D circle, having the light from the sun shining through it, and that's how much the light we have received on Earth, but it has to be shared by a 3D spherical area. So that's why the equation look like this. So again, if you are not sure how you obtain this, then you may want to just derive it again yourself. If you can't, then refer to my video again. The other thing that we would concern before we move on, okay, I guess we are moving on to greenhouse effect. Okay, so is something to do with the albedo. Albedo is basically how much it can be reflected. So a diagram like this, okay, so something that incoming intensity and then get reflected, and so the ratio of it, okay, is defined as the albedo. And so it's something to do with how the greenhouse effect is concerned on a planet, including Earth, of course, and it will vary day to day due to, for example, the weather, the cloud formation, the latitude, and even in a longer time scale, whether or not there are trees, whether or not something become a desert, whether or not it is covered by snow. Obviously, the color has a very important role in terms of the albedo itself, whether or not it's reflective or not. And then it will concern the energy balance model. And so therefore, using the idea of energy balance model, because we expect in terms of calculation, usually we expect the planet would not usually have a great change in temperature. So you expect the incoming intensity and the outcoming intensity should be equal, and therefore the temperature maintain constant. And so that is usually an assumption we make when we have to set up a certain equation for calculation. And that's sometimes maybe they ask you to calculate albedo, etc. So that's something you need to bear in mind. Now going back to a bit more about greenhouse effect in a qualitative idea, first you have to understand the mechanism for greenhouse effect is due to resonance. So I think it's very important for me to indicate an arrow on the side here leading back to waves, okay, the one that we have covered earlier. And I think that's the whole purpose of the new syllabus, as in the past it was not very emphasized in the past. Anyway, so the reason why greenhouse effect is an effect is something to do with the gas which we define, we call them greenhouse gas. Examples are these, okay, which you probably have heard, CO2 for sure. And the mechanism is due to, as I said, resonance. In a more clear wording, you can follow me. That is due to resonance. And if you have to explain more, then talk about the natural frequency of these greenhouse gases match with the frequency of the infrared, because as I said, due to Wien's displacement law, that it tells us that if the Earth is about maybe 25 degrees Celsius, then the corresponding EM wave that they emit is infrared, just like our body, okay, is more or less at that range, will be of the highest intensity. And so these infrared will be absorbed readily by the greenhouse gases because the frequency match, again, resonance, and so they will absorb this energy and they will re-radiate in all directions. I'm sure you have seen those diagrams. And so sort of, you can consider about half of them. It's not exactly half because it's 3D, okay, but I guess you can call about half of them, okay, it's going to go out, continue to go out, and half of them will come back to the Earth. So these mechanisms kind of keep going back and forth. So in other words, having greenhouse gas is like wearing clothes, basically. You don't have to say that in exam, okay? So these are the keywords you may want to follow. And because the syllabus subject guide mentioned about these, okay, so therefore I just put it down. I don't think it's really specific to physics, but I guess I'll just put it down just in case, okay? So what the syllabus point was mentioned is the augmentation of the greenhouse effects due to human activity is known as the enhanced greenhouse effect. So that means having too much of those CO2 and other greenhouse gases, it will means the greenhouse effect is enhanced, as in is getting too much, okay, too bad, and that's causing, for example, summer getting too hot, and then those climate change, other issue as well. And the reason why we have that is could be mainly due to burning fossil fuel, which produce a lot of CO2 and other greenhouse gases. All right, and so now we move on back to more microscopic stuff. When we talk about thermal, we have to talk about the molecular or kinetic theory. So basically in maybe junior, second year, you learn about how scientists theorize everything with particles and then how the particles are arranged, whether they are more separate or closer, forming solid, liquid, and gas. And those things that we have to understand it. I don't think IB would ask you for that level. Okay, so what you really might need to focus on is first two things, microscopically and macroscopically. Let's talk microscopically first, okay? Macroscopic means you can see by eye, human can just interact with it or measure it directly. That is first the state of matter, as I mentioned, okay? So gas, liquid, solid, the free state, which I'll talk about more. The sequence is just because I want to figure out the space. So the other thing that you can see or measure sort of with our own body is temperature. And as for temperature, of course, we have a lot to say about it. But one thing you definitely need to know is the conversion between the Kelvin scale to Celsius scale. This is on the data booklet you can find. And a lot of time when you use the equation later on, then you have to convert it to Kelvin before putting into the equation. And that's why it's sort of a fundamental thing you need to know. Going back to microscopic, this closely linked to the macroscopic view. So first, we can describe or categorize the objects with internal energy, which equal to the sum of two things. One is total random kinetic energy. Okay, notice this is different from the kinetic energy we mentioned in mechanics, the half mv squared. Those are talking about all bunch of particles moving together. Well, this one, it could be just, for example, my phone, okay, sitting here, not moving, but then as we learn, the particle are still having, the whole thing have temperature, and so the particle within the phone will be vibrating at a certain degree that has a certain degree of random kinetic energy. And so we could then describe it, okay, with that. And so in terms of the state, then it's something to do with total intermolecular potential energy. So basically Ke and Pe again, okay, but in a microscopic view, due to different reasons. And so when there's a change in that, sometimes maybe you have heard about temperature change and the state change, then we can evaluate the heat transfer using the two equations. I'm sure you know about it. So for change in temperature, okay, that's something related to the change of Ke, while it's changing the state, then it's something changed with the potential energy. All right, and so that's the only two things you probably can change in thermal, and that make up the internal energy. Now, before we move on to this equation and talk about ideal gas law, let's talk about some building stones of it. So in molecular theory, we could characterize the molecules with some more things, okay? So one is density, how packed they are, so mass over volume. And the other thing is about their pressure, and so force over area. So these are very useful later on when we want to describe the ideal gas. The other thing is number of molecules, because there are so many molecules. So we come up with the idea of moles to describe them. And so this is the equation. So these are some basic stuff that are building stones of building blocks of what we have later on. So now come back to here. This is a very important equation because this bridge, as you can see here, the microscopic and macroscopic world. On the left-hand side is average random kinetic energy, which describes the microscopic view. On the right-hand side is merely just some constant, 3/2 kb constants, times the temperature, which is a macroscopic idea. And so this was very astonishing when it came out, and so it's very helpful as well for our calculation. And so by word, you can also talk about how temperature is also directly proportional to the average kinetic energy of ideal gas. Remember, these equations should only work for ideal gas and monatomic particles. That means like helium, for example. Okay, if you have a more complex composition, then it's not a very good model, according to the assumption. The other thing is average, okay? So that means you are talking about one single molecule or particles only, not a whole bunch of them. If you have to calculate the total kinetic energy, then you must multiply with n, okay? As I always say, the idea of average is like if you want to calculate the average height of the people in your class, is probably having all the height add up divided by number of heads. So perhaps it's something like 1.7 meter, let's say. Okay, and that is a good approximation of one single person height in your class. Is not equivalent to the total sum. Okay, that would be ridiculous. So if you want to somehow calculate the total height, then you have to multiply with, say, 20 people, then multiply 20 people with 1.7. So same idea here. If you want to find the total kinetic energy, then multiply with n. This is just the average. So if you get that, okay, so this is how the linkage is. Okay, multiply with n and get the total, and then the equation can then change to this. Okay, notice that there are different representation. It's just something to do with the number of molecules and moles equation. Okay, essentially they are all the same depending on your convenience. And these also lead us to the ideal gas. And first of all, the reason we want to have ideal gas is we want to have some useful tools. And in the process of modeling them, these are the assumptions. I'm not going to go through each of them word by word. I would recommend you really memorize all of them, 5. Okay, the more important one I put at first. So if you are asked to cite, for example, 3 of the assumption, then perhaps the first 3. Okay, and so these are quite concise already. I don't think I can guess simpler than that. So make sure you really read through this. And because of these assumptions, in the real world, we will find there are conditions where real gas, ideal gas is hypothetical. There's no really ideal gas 100% in the world. So everything is just approximation. So for the real gas, which we can really treat them as ideal gas, so then our equation calculation can really predict, in a very certain degree, then it has to meet the condition of high temperature, low pressure, and low density. The reason why we have this is something to do with the assumption itself, because with these conditions, then it will match with the assumptions very well. Okay, you can think about why. For example, is concerning about the time of the collision. You can imagine the volume itself has to be big, okay, for the container, while the particle has to be really small. So when it travel through, okay, the impact time that they have versus the travel time is much bigger. Okay, that's one of the assumptions, and that in the real scenario, that is something to do with the density. Okay, you have to have a very low density so that you can travel for long and then not going to impact very frequently on the other particles. Okay, and then because we have this model, then we can come up with the ideal gas law. That's the whole point of it. And because we have different scientists like Boyce or Charles, you heard about the 3 laws, then we empirically study that. Okay, and then find out these are maintaining constant in this particular relationship, and then we come up with the PV equals nRT. All right, and so again, depending on what information you have, then you can use it. Just make sure that you use in Kelvin scale. Okay, going back to the very last one to end the SL part, we also have an equation to describe the pressure. Okay, so pressure equals to 1/3 density times the velocity square is something to do with the ideal gas. So remember, this equation can only use for ideal gas. Okay, don't use it for like some other like random stuff like a block of wood moving. No, okay, you cannot. So the pressure obviously refer to the gas pressure. Okay, and the reason, or if you really want to look through the derivation, I'm sure there's a video on the playlist. If you really want, then go for it. Okay, and then it's something to do about the particle, go from one side to another side, like I said. Okay, and then that's linked to the pressure. So when the particle is colliding on the wall of the container, it will bounce back, of course. There's a change of momentum, and that momentum with the change of time constitute the force, and that is the force exerted on the surface of the container, and therefore there's a pressure exerting on it. And of course, each particle will contribute it, and so if you multiply it by the number of particles, then you can find the total pressure exerted on the container, and that's basically how the gas pressure can be evaluated. Very interesting thing, okay? But I guess the derivation, I don't think they will ask you, but it's more important you have this idea of where this gas pressure is coming from. So here is more detailed key steps, okay? Basically what I said just now, that you should be able to explain. So for example, they may say, oh, what if now the temperature increase? Then the first thing you probably recall is because temperature increase, KE increase, velocity increase, and therefore they will be impacting on the wall of the container greater, with greater change of momentum, greater change of force, and therefore greater pressure at last. So these are the ideas you need to outline step by step. Okay, so SL is all done. Now we will go to B4, which is a pure HL topic. So on the side here, I got the thermodynamics. Okay, and then we'll first dive to first law of thermodynamics, and then we'll talk about the second, and at last we'll talk about the zeroth, because the zeroth one is the one that people come up with on this later, after the second law is discovered. But they find it's more fundamental, so they call it zeroth. Anyway, So the first law of thermodynamics is something to do with basically energy conservation. So energy cannot be created or destroyed, only transferred from one to another. You learn about it in mechanics already. However, we are be more specifically talk about this is only true in a closed system. What it means by a closed system, okay, is in a closed system, okay, then you can have this equation, okay. But then in terms of energy has to be maintained a constant, then we have to consider it as an isolated system. So no energy can exchange from inside to outside of the system, no mass exchange, basically the strictest situation. So what you need to know is really how the three different systems names, okay, and what they actually means inheritedly. An open system means the mass and energy both can flow, free flow, okay. So very often we may not be looking at those situations. Okay, so within a closed system, mass maintain the same, but then the energy can go in and out, and therefore we can come up with a description, a model equation on that. And so you can easily find Q is the heat, U is the internal energy, well, change for the delta, and W is the work done. And so in terms of the positive and negative sign, there are different conventions. So in different textbooks you may refer to, of course, if you are reading an IB textbook, then they should all be aligned. But if you look at some other textbook from just other curriculum or other purposes, then they may be using a different definition. So it's important for you to pay attention to what they means, okay, when the values of these three quantities are positive and negative. So yeah, make sure you're familiar with that and you can use it properly during your calculation. So I'll leave this table to you. Now, when it comes to all these three things, heat is more like very passively, okay, what is done on work done and internal energy, and what's left is basically heat. And so the heat is composite of the work done, which is due to the change of volume at a certain pressure. So a simplest idea is, let's say you have a constant pressure, although it may not be constant. Later on we'll get to that point. But let's say the pressure is constant and now you have a volume change, then that will require work done. Just like the simplest idea is you have a syringe and then which is closed, and then you have to push it, okay? So you need to push it hard, okay, in order to really compress it. Or the other way, if you pull it, then it will expand. Again, you still need the force to expand it, which in a way that is a work done. So whether it's in or out, okay, so that is illustrated in this diagram. So the direction, okay, is very important. So make sure you get that. And then the internal energy, as we said, U, okay, here is concerning the delta U. So again, if you are looking for change in internal energy, then you can just find the internal energy before and after. Earlier we have the equation. Remember this one? Okay, this one is to evaluate the actual, the internal energy now, okay, as a state. And for the change, of course, you need to find before and after. So that's why there's a delta, okay, for delta U, and here is delta T, because other things are just constant. So that means there's a change of temperature, then there's a change of internal energy. If temperature change is not zero, then internal energy change is also not zero. Okay, as simple as that mathematically. And so again, what left behind in this equation would be heat. And so you can evaluate with that. Okay, now going back to the second law of thermodynamics, then it's something to do with entropy. Okay, so you can read the statement here. You should recall this directly if you are asked to. So basically, entropy is always increasing for spontaneous process. Spontaneous means it just happened naturally, basically. So entropy, okay, symbol is S. In a rather ill-defined way, although IB adopted that, okay, it's called the degree of disorderness of the particles in the system. And in the real isolated system, the entropy is, the system itself, the state is always irreversible, and therefore the entropy increase, and that tells us the direction of the event, and which is called the error of time. Okay, is a name suggested by scientists. The entropy in a non-isolated system might decrease locally, okay, or you can say it can decrease locally, but as a whole, globally, you can see that the entropy still increase, okay, because it's decreased only in local way. You probably have put in some energy to do that, and so that's the law we have discovered, okay. And so for entropy, in fact, the better way we could describe, I would say the best would probably be this one, okay, which from Boltzmann, linking between the microscopic and macroscopic state. And so the way is we can then evaluate with this approach. The omega, okay, here means the microstate, and then we can then use it to calculate. So in terms of macrostate and microstate, then you could then look at this example of how head and tail of coins can be flipped. So the microstate means that all the possibilities you probably you learn in mathematics. How maybe you have two head, two tail, and one head, one tail, or one tail, one head. Okay, 4 microstates. However, having one head, one tail, or one tail, one head is the same macrostate. Okay, because you don't care about the sequence, okay, it's just the same as the two, okay, so macroscopically they are same, but microscopically you know there are two different scenarios. So when it comes to, in a broader sense, maybe have more coins, or you may not just work with coin, but also particles or things, or even switches. IB Physics expect you to do these simple counting. Okay, so do expect things like that may happen. Although they shouldn't give you a very complicated scenario, according to the subject guide. We have never seen it before because it's a new thing in the syllabus. So let's see. The other equation that you can use to talk about entropy, okay, is this one. Notice that this is a change of entropy, and so this is just more in a microscopic way that you can evaluate it. Now, in the later part of this, we talk about thermodynamic processes. There are 4 processes. I'm sure you could recall. Okay, isovolumetric and isobaric, isothermal, and adiabatic. And so each of them will mean something is constant pretty much. Okay, so same constant volume, constant pressure, constant temperature. This one is a bit different. Okay, it's not constant but no heat transfer, and that is Q equal to 0. As for the other 3, by applying the first law of thermodynamics, this equation, then you may reduce the equation to something simpler probably. So for example, if volume is a constant, referring back to the work done equation, which you need the delta V to be non-zero, but if it is 0, then work done is 0, and therefore the equation will be reduced to this. And then if the temperature is constant, then internal energy will be constant, and therefore the change is 0, and therefore you reduce to this equation instead. While for pressure, okay, it's a bit tricky because when the pressure is constant, remember we still have this diagram, right? So in other words, you still have a change of volume. And that will mean you didn't actually reduce the original equation here. It's just that you know it's constant pressure. So you might be doing some calculation with that easily with just a rectangular shape, because if it is not continuous, then you basically need calculus to calculate. So the idea of this is just simply you can then evaluate the work done more easily. But you still need to deal with the whole equation. While for adiabatic, then Q is 0 directly in the first law equation, and therefore you reduce to this equation. Okay, so different consequence you will have. And now you would then be able to describe the 4 processes on the graph, okay, the PV graph. And so again, you need to identify which one is which one, and especially it may be tricky when it comes to isothermal and adiabatic, because they both are curved, while the other one is just horizontal and vertical line, which are very easy to identify. One thing you need to recall is the adiabatic curve is steeper than the isothermal curve. The reason is something to do with this. Okay, so I guess you probably just memorize it really. Okay, it will help. Okay, in exam because you don't have that much time to think. But the underlying reason is something to do with this equation. So going back a bit to the adiabatic. So first, for adiabatic, there are two kinds. One is expansion. Okay, one is compression, depending on whether the volume increase or decrease. And then the effect, okay, is very definite. Okay, then you can see here. Okay, when it expands, the temperature will decrease, just like how the gas when you go to higher altitude in the mountain, then you get colder. And then for the compression, okay, it will basically have the temperature increase. So if you have seen those fire syringe, okay, that you combust it and basically sort of combust it, okay, you compress it, I should say, then you can make a fire, like small fire out of that. The whole equation you can describe, okay, is like this. The derivation is not really required in IB Physics. But you really need to know one thing, that is in the data booklet you have this equation, but this is only for adiabatic process. Okay, and if you are looking at another equation, which is Boyle's law, you have learned maybe in earlier years, or you can deduce it from ideal gas or PV equals nRT. You may come up with an equation of PV equals PV. However, if you think about the whole ideal gas or PV equals nRT, this PV equals to PV thing, 1 and 1, 2 and 2, of course, Boyle's law, it only works for constant temperature. So only if temperature is the same, then you can have this one. While for adiabatic, it's not. I mean, we just talked about the temperature change. Okay, so it will never have these two equations work together. Okay, if you are having a adiabatic situation, then use the one here. If you're having temperature constant, then use the temperature on the left. However, remember the ideal gas law still works. So PV equals nRT still work in both situations. Now, because we have these four, okay, then we could possibly make the heat engine. And the first thing that you have to know about the heat engine is it's an engine. Okay, it continuously run, and so we have to make cycles. So that will mean that you have to go back to the original state on the PV diagrams, and so that will make it a cycle, right? Okay, and so in terms of a cycle, of course, there are lots of things going on, which we just cover. At the same time, there's a big part on something called the Carnot cycle, which is an idealistic way to consider what would be the so-called most efficient engine. And hypothetically, we are including 4 reversible processes, because we talk about entropy, and if you remember the things with entropy increases, then their process is irreversible. So in order to maintain the entropy the same, okay, so that the change is 0, we would need to use reversible processes. So the only possibility, so that we can make a cycle out of it, is using this 2 isothermal and 2 adiabatic. Okay, you cannot use the other 2 to make it. It's not reversible that way. Okay, again, the whole purpose of this is just think of the limit. Okay, so then the entropy change is 0, and so then with this, then we may concern that, as I said, the efficiency, okay, is basically the limit, and so we have to go back to consider the efficiency equation. This is just the one that I copied from mechanics, and using this general equation, which is the definition, okay, then we can derive this equation for the Carnot cycle or Carnot engines, okay, which are concerning about the hot end and cold end temperature. You can see that these give us the insight, okay, because this is 1 minus the ratio of them. The efficiency can at most be 1, because obviously this can only be 0 at most. You cannot have something higher than 1, in other words. Even if we want to make the whole thing as 1, it will mean that you will need and infinitely high temperature. So then this would divide like infinity. Okay, I know it's not going okay in math. Okay, or you have to use basically absolute zero for the cold end, which is basically telling you that is also impossible in the real life. Not to mention, in fact, the process will take a really long time to do the transfer, and so it's also not realistic. So that's why we have so many other engines in the world, and we are not just simply having just one engine, which is so-called the most efficient. Okay, and so I believe that is all for the concept map. So stay tuned for the next one. I'll see you again next time.